as far as the sentences in our toy language L simple are concerned, we found what we were looking for: a formally correct and materially adequate definition of truth. Everyone who understands the everyday expressions Socrates, Plato, Aristotle, Tarski, is a philosopher, is a teacher of, the logical expressions not, and, or, for all, with the relevant variables, if then and if and only if, who understands the mathematical term set, who understands in addition the syntactical expressions name in the vocabulary of L simple, predicate in that vocabulary, and sentence of L simple, and who knows the relevant English grammar of our definition, can also understand the definition of truth for L simple, and hence understands truth for L simple. While L simple has been really simple, Tarski actually provided similar kinds of definitions of truth for much more complex languages. Languages with much greater vocabulary. Vocabularies that might include the usual names and predicates from, say, mathematics, physics, and history, and more. Languages with more logical symbols, such as if then, if and only if, for all, there is, and more. Languages with more complex grammar. Languages with sentences that speak about infinitely many objects, such as the natural numbers, or all sets of natural numbers, and so forth. While accordingly, the definitions of truth for these languages are more complex than our definition of truth for L simple, they are equally doable, and the construction of the corresponding definition is based on similar methods. In particular, stating a recursive definition of truth, and then turning that recursive definition into a standard, so-called explicit, non-recursive one. I will not state any of these more complex definitions of truth for more complex languages here. Instead, let me show you what further conclusions we can draw from our definition of truth for L simple. First of all, L simple is not that simple. Its set of sentences is already an infinite set. This is because by applying the logical symbols over and over again to sentences in L simple, one gets longer and longer sentences of L simple. And there is no end to this. Indeed, one can prove that the set of sentences of L simple is of the same size as the set of natural numbers, in the sense explained in the last lecture. There is a pairing off between the members of the two sets. So our definition defines truth for infinitely many sentences in one fell swoop, which is not that bad. Secondly, once one has stated the definitions of sentence of L simple and truth for L simple as precisely as it was done above, it becomes possible to prove general claims about truth for L simple by means of similar methods as those by which mathematicians prove statements about all natural numbers. Mathematicians prove that all natural numbers have a certain property P by first showing that 0 has that property P, and then by proving that for all natural numbers n, if n has the property P, also the next greater number n plus 1 has that property P. By the so-called principle of complete induction over natural numbers, which has nothing to do with inductive or probabilistic reasoning, it follows from this that all natural numbers have property P. For 0 has P, and if 0 has P, also 1 has the property, and if 1 has it, also 2, and so on throughout all the natural numbers. Similarly, in our case, one proves first of the simplest sentences, like Socrates is a philosopher, that they have a property P. Then one proves, for all sentences x of L simple, if x has the property P, then also the result of putting together the logical symbol it is not the case that with x has property P. And similarly, for all sentences x of L simple, for all sentences y of L simple, if x has the property P and also y has the property P, then the sentence of L simple that results from putting together x with n and y has the property P. And finally, for all sentences x of L simple, for all sentences y of L simple, if x has the property P and also y has the property, then the sentence of L simple that results from putting together x with or and y has the property P. By the principle of complete induction over sentences in L simple, it follows from this that all sentences of L simple have property P. For the simplest sentences have P, and if they have P, then also the sentences that can be built by applying a logical symbol to them have P, and if those are P, then also the sentences that can be built by applying a logical sign to them have property P, and so on, throughout all the sentences of L simple. We know that we reach all sentences of L simple in this way by the definition of L simple that was stated above. What justification do we have for these principles of complete induction? Well, either one simply takes them for granted as axioms, as it were, and no mathematician would complain about that, or even better, one derives them from set theory, which is possible. As mentioned in the first lecture, set theory forms the foundation of modern mathematics, and the principles of induction above can be shown to follow from it. Here are two examples of theorems that one can prove by the method of complete induction over sentences in L simple. Theorem: for all sentences x of L simple, the result of putting together a quotation mark, the sentence x itself, another quotation mark, is true, if and only if, and the sentence x again, that thing follows from the definition of truth for L simple, if taken together with the definition of sentence of L simple and basic facts concerning the grammar of these sentences. In other words, every truth equivalence for a sentence of L simple follows from the definition of truth for L simple. The definition is provably materially adequate. Intuitively, this was already clear from our examples from before, but it is one thing to be intuitively clear and another thing to actually prove things. Second theorem: for all sentences x of L simple, x is true, or the result of putting together it is not the case that with x is true. In other words, for every sentence of L simple, either the sentence is true or its negation is true. The last theorem shows that our definition of truth is not just useful in the sense of determining the meaning of true in a formally correct and materially adequate manner. It is also useful in the sense that one can derive general laws of truth from it, such as, for each of the infinitely many sentences of L simple, either the sentence is true or its negation is. I had mentioned that little law of truth already at the beginning of this lecture when I distinguished truth from belief, but it is one thing to mention it and another thing to actually prove it, in a manner that is just as precise as the mathematics of natural numbers. Let me illustrate the method of proof by induction over sentences of L simple by sketching the proof of the second theorem. The first theorem I will simply take for granted now. So here's the proof. The property P in question here is x is true, or the result of putting together it is not the case that with x is true. First we prove that the simplest sentences of L simple have property P. For instance, by logic, Socrates is a philosopher, or it is not the case that Socrates is a philosopher. We know already that the truth equivalences Socrates is a philosopher is true if and only if Socrates is a philosopher. It is not the case that Socrates is a philosopher is true if and only if it is not the case that Socrates is a philosopher, follow from the definition of truth for L simple. By substituting equivalent sentences for each other, we get from Socrates being a philosopher or Socrates not being a philosopher, Socrates is a philosopher is true, or it is not the case that Socrates is a philosopher. That sentence is true. Hence, the sentence Socrates is a philosopher does have property P. Analogously for all the other maximally simple sentences of L simple. Next we prove, for all sentences x of L simple, if x has a property P, then also the result of putting together it is not the case that with x has property P. In order to be able to state this part of the proof more succinctly, I will abbreviate the result of putting together it is not the case that with x by negation of x. So we will prove for all sentences x of L simple, if x has the property p, then also the negation of x has property p. Okay, assume x has property p. So x is true or the negation of x is true. We need to show now that in this case also the negation of x has property p. Negation of x is true or the double negation of x is true. By assumption, x is true or the negation of x is true. Assume the second to be the case. The negation of x is true. Then we are done. For that means, by logic, even more so, the negation of x is true or the double negation of x is true. And this is what we needed to show. Now assume the other possible case, the first case, x is true. By logic, this is equivalent to x is not true. Or, formulated differently, it is not the case that x is true. Or, again, reformulated, it is not the case that x is not true. It's all equivalent. In any case, whatever the x, the truth of x is doubly negated here. By the definition of truth, x is not true if and only if the negation of x is true. By substituting equivalence for equivalence in the context of it is not the case that, it follows, it is not the case that the negation of x is true. Here the truth of the negation of x is negated once only. But now we can apply the definition of truth again. Whatever the x it holds, it is not the case that x is true if and only if the negation of x is true. This also applies to an x that is itself a negation sentence, something of the form negation of x. We can get rid of the it is not the case that and plug in another negation symbol in front of the negation of x as compensation. In other words, by substituting equivalence for equivalence again, it follows that the double negation of x is true. But that implies, by logic again, the negation of x is true or the double negation of x is true, which is what we needed to show. In either case, we derived what we needed to derive. So under the assumption x has property p, that is x is true or the negation of x is true, it does indeed follow that also the negation of x has property p. That is, the negation of x is true or the double negation of x is true. The two remaining cases of sentences of L simple connected by and sentences of L simple connected by or are similar to the case of negation. One only needs to distinguish 4 cases now instead of 2, but that is all. So we are ready to apply the law of complete induction over sentences in L simple. From it, it follows that all sentences of L simple have property p. For every sentence x of L simple, x is true or the negation of x is true. We have derived a general law of truth from our definition of truth, the definition of sentence of L simple, some rules of logic, and the method of proof by complete induction. An almost arithmetical proof in the service of a philosophical account of truth.